everyone, welcome to this manufacturing process technology part 2 module 16. We will be discussing altogether new advanced machining process today, which is the ECM or the electrochemical machining. So this process, electrochemical machining, is typically it's you can call it the reverse of electroplating, which is a very common process used in the industry. And here the idea is that you have a redox reaction, because of which there is a deposition of one kind of material on the surface and alternately the taking away of another kind of material. So the material because of electron flow maintained outside the flow cell or the electrolytic cell is basically dissolved in one side and deposited on the other side. Now think of it that in this electrolysis process, if the material were to be dissolved on one hand, but somehow be precipitated so that it does not get deposited on the other electrode, then it would be a machining process typically. So that is how electrochemical machining is realized, and there are a lot of modalities associated with this process of electrochemical machining. It is a die sinking process. So whatever is the shape or size of the electrode, it would create just a negative map of itself on the surface that it is machining. And so you can consider this to be a die embedding in nature, or the die gets embedded into the surface when we talk about the material removal through electrochemical means. Okay, so in brief, the electrochemical machining is a process which is the reverse of electroplating with some minor modifications. I am going to talk about that in great details. They are based on principles of electrolysis, and this typically comes under the ambit of Faraday's laws of electrolysis. So we will try to estimate the material removal rate using some basic principles of electrolysis and Faraday's laws that has been suggested probably almost 1 century back. So in a metal, electricity, as you know, is conducted by free electrons, and typically the conduction and the valence bands have more or less overlapping energy levels. But in a solution, the conduction of the electricity is attained by the movement of ions. Okay, so these are free moving objects. There can be negative ions, there can be positive ions, where typically it is one electron excess or one electron deficient, or even multiple electron excess and multiple electron deficient, depending on what is the valency that is there in the solution. So all the charge across the solution is typically carried by the ion movement. So when we are talking about a solid which is in interface with such a liquid, you have to understand that the problem which lies there in the basic physics is that on one hand the charge carriers are the electrons and the holes, which are bound to the orbitals or bound to the nuclei, which are participating to formulate the solid bond together. And on the other hand, on the solution side, it is basically the ion transport which happens. So there has to be a balance between two completely different physics which is involved in transportation of ions vis-a-vis transportation of the electrons and holes within solid. And so there has to be an interplay between the ion transport processes of the solution and the solid, and that is what makes this whole electrochemistry very interesting, where there is a formation of some kind of a dual layer across which this charge transportation takes place, and we will do in details about all that theory when we talk about ion transport equations. Okay, so the flow of current through an electrolyte is always accompanied by movement of matter, and in an ECM process the workpiece is connected mostly to the positive electrode, tool to the negative terminal. So the idea is that the electrode or the workpiece would be responsible for sending out the ions to the solution, and if we can somehow be able to precipitate those without getting deposited onto the tool side, we are left with a process which is subtractive in nature, or a machining process as such. Figure below shows a suitable workpiece and a suitably shaped tool, and you can see that this is the start of the process. So this is the beginning of the process, and this is how it looks as the process goes to equilibrium. Okay, so you may have a question as to why it's a die sinking process, or in other words the flat surface here on the tool has been converted typically the negative shape of the tool surface. So here is the answer to this kind of a query. So if we look at the Ohm's law, which takes place even in solution, just as it takes place in solids, okay, obviously the conductivity levels are very different in solution as opposed to solids. The conductivity is too high in solids, in comparison to that in solution. So by the Ohm's law, the voltage V is represented through the current I times the resistance of the flow path of the charge. In this case the flow path is the solution, so we are talking about the solution as a flow path of the charge. And so if I were to consider the resistivity the resistance in terms of the resistivity rho, so we can say that resistance is rho times of the distance of separation d divided by the area of the interface, so if the electrons are, or the current is transported in vertical direction, let's say from the cathode to the anode side, okay. So the interfacial area is really the area of the workpiece which is being exposed to such an electron flow in the perpendicular direction to the path of the electrons, or to the flow of the electrons. So I'd say that V becomes equal to I times of rho d by A, and in other words we can call this as I by A times of rho d. I by A is the current density, and we have resistivity here times of the distance of the inter-electrode spacing, okay. So this is the distance of the inter-electrode spacing. So excuse me. So if I am wanting to find out what is the field across this gap, so the field would definitely be equal to the voltage per unit length, or the potential difference per unit length. So that is how the electric field is represented. And so in this case the electric field would be written as J times of rho, okay. Our electric field is equal to the current density, current per unit area, times the resistivity of the medium. So obviously if I were to look at this shape at the start of the process, and we have different values of d, let's suppose in this particular case we have a d which is very close to the workpiece, okay. So let's say for instance this particular distance d is small, okay. On the other hand the distance d here, let's call it d1, is quite large, okay. So obviously the electric field at the center here would be more in comparison to the electric field at the side. So if the electric field E at the center here, let's say is E at the center, and this is, let's say, the electric field at the side. So obviously the E center is much larger in comparison to the E side. So obviously the current density, which is also sort of reflective of the material removal, would actually be higher at the center. E, obviously as you see here, the electric field E is proportional to the current density. So at the center obviously the current density would be much larger in comparison to that at the side. So therefore the material removal would be much higher at the center in comparison to the side, which is what is visible in this equilibrium case. So after some time, when equilibrium happens, you can see that the field has almost equalized, whether it is center or side. the field is more or less same here as opposed to here. So, E center is actually equal to E side. Okay. In other words, the current densities are same. Okay. So, that is one of the reasons why there is an inverted shape of the tool which is imprinted upon the workpiece when we are talking about electrochemical machining, and typically that is the reason why this kind of process is known as a die sinking process. So, let us learn a little more about electrochemical machining. The electrochemical machining process comprises of a tool which is provided with constant feed motion. Obviously, this part I have already made clear that how it is a die sinking process, and workpiece assumes the same shape as that of the tool. So, the electrolyte is pumped at a high pressure through the tool and a small gap between the tool and the workpiece. The electrolyte is so chosen that the anode is dissolved, but there is no deposition back on the cathode. So, that is how it is a micro machining or a machining process. Whatever is dissolved goes as a precipitate and is carried away by the circulating electrolyte. And the order of the current and voltages in this particular case are about 1000 amperes, about a kiloamp current, and 8 to 20 volts. And the gap is of the order of about close to 100 to 200 microns. The metal removal typically is about 1600 millimeter cube per second for each 1 kiloampere current. It is actually an energy intensive process if we talk about mechanical vis-a-vis this form of energy, but you have to understand that the reason for non-conventional processes is because you are dealing with tough materials like tough alloys on one hand. Another is that you are also trying to make as complex geometry as can be possible, and sometimes with conventional machining that capability may not arise. Okay. So, approximately 3 kilowatt hour power is needed to remove about 16,000 millimeter cube of metal, and this is about 30 times the energy required in a conventional process. So, it is almost 30 times more expensive in terms of energy utilized when we talk about electrochemical machining. So, let us look at approximately how this electrolyte flow would happen in conventional electrochemistry, electrochemical machining system. You have a tool which flows the electrolyte from the center to the sides. Okay. So, there is a emanation and a flow of the electrolyte from the coaxial center of this particular tool, and it goes and it spreads across the workpiece and then tries to escape from the gap between the workpiece and the tool. There are insulations which are put in to ensure that you do not get a taper, which is a major problem in ECM sometimes. There is a splashed electrolyte and it creates a lot of defects, as I will be explaining in great details later on. And typically this tool needs to be at a constant feed motion, so that once the equilibrium gap is established between the tool and the workpiece, the motion and the way that the surface recedes, or the workpiece surface recedes, are sort of equilibrated to each other. Okay. So, that is why it is called equilibrium gap. And obviously the workpiece, needless to say, is made the anode, and the tool made the cathode, and a low voltage high current DC supply is used for feeding the process. So, with the ECM, the rate of metal removal is independent of the workpiece hardness. So, you can go as hard as possible on the material front and still be able to do machining, which may not be the case in case of mechanical removal. ECM becomes advantageous when either the work material possesses a very low machinability, or the shape of the machined item is very complex. I have already discussed about this, and unlike most other conventional and unconventional processes, here the tool wear is very limited. There is some tool wear, but practically very less tool wear. Tool wear, whatever is here, is mostly because there is some kind of warping. You can think of the gap between the tool and electrode to be too small, where there is obviously a velocity head at which the electrolyte flows, and so there is some kind of a electrolyte pressure which creates a tool deformation. In any event, you have to choose the parameters in a manner so that such deformation does not go anywhere. That kind of a pressure which is generated does not go anywhere near the ultimate yield strength of the material, where there may be warping in the tool, etc., which is happening, which happens. So, this is a very critical situation to be looked at, or a critical design aspect to be looked at whenever you are designing electrochemical micro machines. Okay. But as of now, we are more concerned with the process at the macro scale in totality. So we'll probably keep this towards the later part of the lecture, when we'll talk about how pressure and stresses, ultimate yield stresses, need to be equalized for designing the velocity at which the electrolyte needs to flow between the tool and the workpiece. So this is basic theory about electrochemical machining. Let us now get into the physics of the machining process and try to estimate the material removal rate. So as I earlier described, the governing laws for this electrolysis process are typically the two laws proposed by Faraday. The first law says that the amount of chemical change produced by an electric current, that is the amount of any material dissolved or deposited, is proportional to the quantity of the electricity that is passed. And the second law says that the amounts of different substances dissolved or deposited by the same quantity of electricity are proportional to their chemical equivalent weights. I am going to come to this, what chemical equivalent weight means, gram equivalent weight. So in quantitative form, obviously the mass which is deposited is a function of the current time product, which is the amount of charge which flows in. So here the argument that is provided is, supposing there is exactly 1 mole of univalent ion which is deposited or dissolved into the solution, exactly 1 mole of charge should flow from the anode to the cathode to keep external charge balance. Okay, and so therefore the quantity of charge that is involved there is obviously going to define how much mass is going into the solution. So the other important issue here is the gram equivalent weight of the material. So the gram equivalent weight of this material is basically the atomic weight divided by the valency of the particular ion. So if I am talking about, let's say, the Cu plus 2 ion, okay, cuprous ion, then the atomic weight of copper divided by 2 would be the equivalent weight of the copper, okay, plus 2 ion. So that's how the equivalent weight is mentioned. So if I were to look at this equation, the underlying logic is very simple, that the amount of charge that is involved, or the charge transport that is involved, is really the current time product. So this is actually the number of coulombs, right, which is flowed. And supposing if I wanted to have the cuprous ion to be balanced, so in order to generate cuprous ion out of copper, you exactly give out 2 electrons, right. So somehow, if this factor can be put in the number of available charges available here are so many coulombs, okay. So if I wanted to multiply this by the number of electrons, for example, I know that in 1 electron the total amount of charge that it carries is let's say 1.6 into 10 to the power of minus 19 coulombs, okay. So if this is the electronic charge that is there, so how many moles of electrons are available in this coulomb would actually be another term which is known as the Faraday constant, okay. So charge of 1 mole electrons. So in a way, I am trying to see whether what is the availability in terms of number of moles, and I know that 1 mole of charge exactly coming out of the system would generate 1 mole of the particular ion, and 1 mole of this particular ion or let's say the material that is being converted into ion and electron constitutes its atomic weight, okay. So there is a relationship between the charge and the number of charges needed per species to get converted into the corresponding ion, okay. And then there is that if 1 mole of such charged species is spent, an amount equivalent to the atomic weight of the material will be coming out. So that's a relationship between mass and charge which is being made through this Faraday's laws of electrolysis. So let's now before going ahead start to delve a little bit into the ion-ion and the ion-solvent interaction wherever there is an electric field given to, let us say, a solution which is present, and it is comprised, otherwise it is electrically neutral, but it is comprised of all the positive charge centers and the negative charge centers. Let us say NaCl solution. So we have Na plus and Cl minus, well dissolved because the water is a dielectric. So therefore there is a tendency to split up these ions into Na plus independent ion and Cl minus independent ion, and we want to find out what is the ion-ion or the ion-solvent interaction, okay, between the various positive charge centers and various negative charge centers. So although strong electrolytes are completely ionized, their ions are not entirely free to move independently of one another through the body of a solution, except when it is a infinitely dilute solution and the mean free path is almost infinite for an ion to move. So the following things or events may happen in such a situation. Number one obviously is that the ions would have their own random walks, which are because of thermal motions or Brownian motions, where the ion would actually, let us say there are positive and negative ions which are there in a medium, okay, and so there is always a random walk that such ions would make, and each ion would have its own track or trajectory, and that is one kind of motion that is prevalent in such systems, and it's of course a function of the temperature state that the system is in. There are Coulombic forces between the ions of same and opposite kinds. Obviously there would be forces of attraction between the positive and negative charges, and similarly forces of repulsion between two negatives or two positive charges, and so this will be present, which leads to a time averaged ion atmosphere of one kind with respect to a central ion of the opposite kind. Here, as I was drawing this figure, as you see here, there is obviously we have these polarity differences maintained. So a positive ion in a close proximity of a negative ion. So if I were to consider only one positive ion, there in fact would be a situation when it is engulfed or surrounded in many negative ions together, okay, and that's how you can say that it is a one central charge followed by the other charge of the opposite kind as its cloud, or its environment. So this would be one state. One state obviously is the temperature based movement of the ions, and the other is that the movement of such ions under an external electric field will be very slow. So the atmosphere moves to the opposite direction as the primary central ion. So now I apply a field here. Let us say I make this positive, this negative. So obviously the positive charge will start moving to the negative electrode, and vice versa, the negative will move towards the positive electrode. And so if there are many such charges and many such environments, there is a continuous making and disruption of such charge environments for these charges to migrate towards the electrode of the opposite kind, okay. So you can think of that movement of such ions under external electric field will be very slow. Atmosphere moves to the opposite direction as the primary central ion, resulting in a continuous disruption and reformulation of the atmosphere, and the atmosphere is kind of asymmetrically distributed around the central ion, and there are many effects like electrophoretic effects, that is the movement of a charge in a solution which has exactly the other kind of charges, and there are also effects related to viscous drag of the atmosphere. Mind you, this is all in fluid, so therefore any movement of any particular ion would definitely have a drag force which is exactly in the other direction. So this is how the whole ion space is now defined, and we want to now find out what is going to be the implication of let us say if we consider a certain distribution per unit volume at infinity, what is going to be the implication of a certain positive charge and its ion atmosphere because of completely zero electric field at a distance infinity from that charge. So basically we are trying to arrive at the transport kinetics, and this is also known as the Debye-Huckel equation, which was formulated way back in 1920s, and so this we call as the ion transport kinetics. So, we have a positive charge somewhere here, and we have a distribution which is, let us say, far away from this at, let us say, x equal to infinity, okay, a certain distribution of the positive charges and the negative charges. Okay. So, this is actually number density. So, we have positive ions per unit volume and negative ions per unit volume are infinite distance from the central charge, central positive charge, as shown in this particular case. Okay. So, if I wanted to bring a positive charge from, let us say, infinity, the total amount of work done in order to move such a charge to a distance a, let us say OA, in the near vicinity of the positive charge, would be dependent on really what charge is being moved. So, supposing there is a charge which has a valency Z plus. So, therefore, the total amount of charge that is there on this particular charged entity is Z plus epsilon. Epsilon is the electronic charge. Okay. So, if I am wanting to move this pretty close to this point A here, where there exists a field psi A. So, the total amount of work done for positive charges would be given by plus Z plus epsilon psi A, and that for the negative charges would be given by minus, obviously the charge value is minus in this particular case, minus Z minus epsilon psi A. So, this is the kind of work that is done to move either positive charges or negative charges in a way that you can assume that negative value here means that the system is doing work on you, and then the positive value here means that you have to do work on the system for bringing a positive charge close to a positive charge center. So, with this model on board, in the next module what we are going to do is to understand what is going to be the final number distribution in this region A, okay, and what is the kind of potential which will be generated because of that number distribution in the near vicinity of a charge somewhere located somewhere along the solution. So, once we have that figure, we can simply extend that to the case of a solid liquid boundary and can formulate something which is also known very commonly as the zeta potential of a solid. So, with this I would like to close this particular module. In the next module we will try to further solve these transport equations. Thank you so much.